Recording is now in progress. Good evening, y'all. It's Code Platoon. This is golf, evenings and weekends. We're on week 16, day 3, and we're going to do an intro into building a type of a learning model, specifically a binary learning model. You have at some point interacted with these without knowing about it. Who has ever had to go look in the spam folder for something that wasn't spam? It's probably happened to a lot of us, right? It happens when I try to get y'all signed up for GitHub. Sometimes I go straight to the spam folder. Well, that is probably, in fact, I know it is, built upon a binary learning model. Basically, data comes in, a list of words, it is broken down to numbers, and there is a trained model that is saying yes, spam, not spam, with some more going on. But its output is yes, no. There's not, I think this is possibly a tiger. Like that's a different thing. We're not doing anything like that. Or like this is like 90% chance, probably a hot dog. This is going to be a yes, no. There's no in between. And that's what it's trying to answer is a yes or no question. And then we do something with that. This is one of the simplest ones to kind of pick up, which makes it good for talking about. It's good for understanding. It can be a little difficult to grasp how you would build larger stuff than this, but it's going to get a lot of the terminology used that we do want to talk about when we're talking about neural networks, and that is the purpose. Get us used to some of these concepts. Binary learning models are a fundamental type of machine learning models, like I spoke about. We'll be using PyTorch to basically randomize some weights and some biases, and utilize that to take some input and spit out a percent chance of it being accurate. We'll get into training at a later lecture. This one is going to be a very abstract, but hopefully not too abstract. So I try to give examples of what we're looking at here. I talked about email. There's actually other good things on here, but generally email spam detection is the one that I remember. Medical diagnosis, disease or no disease, binary sentiment analysis, positive or negative. Yeah, that's just the same thing as binary. Here is what we're going to start with. The input, well, it's a bunch of random decimals and arrays and junk. It's a matrix. Do y'all remember Boggleboard? We did Boggleboard. We still do Boggleboard, right? Don't
Terrible.
look, don't shake your heads like we don't do Boggleboard anymore. Goodness, do we really
Talking about the
not do
game?
that? Well, it sure was part of the curriculum, and I thought that was something. But you know what? I don't remember Boggleboard. So a matrix, this is just an array of an arrays, right? We're going to use arrays to build a 2D model. This is a list of 3. This is a list of 3. This is a list of 3. There are 3 lists inside this list. You can make a checkerboard kind of thing going on here. That's what I want you to think about with this data. Don't worry too much about all these specific numbers. They don't really mean anything right now because we don't know where they came from. But if you want to think about how random weird numbers could be used, here's a good example. If I were to, oh man, how can I quickly draw something? Do I have,
There's a whiteboard on the Zoom tools.
what will they think of next? Annotate. Uh, what what letter is this, Sean?
Excuse me?
What number is this? Jeez
Yeah,
Louise.
8. I thought that was a
Yeah,
trick question.
that's
I'm
right.
like, what the hell you say?
That's right. That's right. What number is this?
An 8.
These are the same number? How do you know that? They look nothing alike.
Right. But one has a small circle on top.
Yeah, but how did you determine that that's an 8?
Because if you didn't have that little small circle on top, it wouldn't be an 8.
Also,
Sure.
there's a previous 8, so common sense would dictate it was a repeat.
Okay, fine, sure. But like if I could have drawn any other number, you'd have to make some guesses, right? We are doing this kind of stuff. What we'll be talking about here, we're taking an input, we are running it against our brain's known things, right? Like stuff that we have experienced in our entire lives. This network, our neurons are working together and we're making some educated guesses, right? What if I was like, actually, no, that was supposed to be a 0 and I messed up? Like, that would be fine. And you would account for that next time I asked you, right? But that is going to be, you're going to have to, when we're talking about like weights and biases, weights would be like, well, I've been alive for a while. I know, dadgum, you've got a circle on top of another circle. That's probably an 8. And then if I tell you, no, that's not an 8. When it looks like an 8 and it's messed up, that's a 9. We're going to have to count for that for the next time around. That's where we're going to get into things like biases. But ultimately, you're going to make a determination. It's either going to be right or wrong. These kind of numbers could account for, I don't know, if we had like 728 of them, they could be pixels on a screen, right? And the pixels RGBA, like RGBA, yeah, the color coordination, the color, right, of that specific pixel, it's not going to be 0.23, but we could have a decimal representation for that. So this could very well be a matrix. This would be a very tiny little screen, a 3 by 3 screen. But imagine if this was a, a pixelated screen and these were number values of colors. Well, one would just probably be like black or white, but if there were, different colors going on, it's going to get more complicated as the colors change. Just imagine these numbers being, for our example here, a representation of colors changing on a screen, right? That it's a matrix. We're building a 2D object out of our arrays. That's what they could stand for. You then will make some educated guesses with some maths, right? These hidden layers here are just going to be numbers that are running against the inputs. It's being basically a yay or nay. This is still an 8. This is not still an 8. Please don't do that, Zoom. And if that particular, check is a pass, it'll pass it on. So we have 3 checks here, 2 checks here, 1 check here. Ultimately, is it an 8 or is it not an 8? That's the binary check, right? We'll get more into it. That's kind of how I want you to think about it. God, stop. How do I get out of this, y'all? Oh, is it just there for good now?
Jordan,
Oh, yes.
so it I guess it would seem okay when you so these hidden layers I, I would have other software that's looking at these images.
Software, let's say numbers, right?
Well,
Um,
so we are passing in numbers that represent an image. That's what you're saying?
yeah, in this example, but they could represent anything. It could be a text represent or sorry, a number representation of text. If we were talking about emails, spam folder, maybe the word hello is, for our cases, 0.23, and maybe that's just what it stands for. We have to get these things into numbers so you can use math.
So this a particular software, these hidden layers, is that something that we are developing, or this is like from a library already that is using what we are inputting into it? Like the numbers, the images that are being changed into a number, which is
Yes.
happening, is that something that is happening before it reaches the hidden layers, or that's something that happens once it reaches the hidden layers? But if it's something that is happening before, that would be something that we would have to develop then?
Yes, you're going to develop your input. We will decide what these numbers are, and we'll get to that. All this other stuff in here is at first going to be random mathematical numbers, and then we will go on to train it and say, hey, that's a good guess. Hey, that's a bad guess. Adjust these numbers. These are real numbers. I'm talking about them like they're abstract numbers. We're going to legitimately see these work to give you an idea of that. But these are numbers that we will not decide, and then we will kind of reel in. Let's continue on. I think it's better to see what comes next. The input layer, as you can kind of see, receives the data. These hidden layers, they're what's processing this input data through weighted connections and apply an activation function. Hidden layers are where the model learns to recognize patterns in the data. This is just formulas in a way, is the way I describe it. This is just a formula for guessing yay or nay. Activation layer. These layers apply a nonlinear function to the data, allowing the network to learn complex patterns. And output layer, that's in this case, and you know, depends on how you kind of build it, a yes or no, 0 or 1. Was that good or bad? Rather, it'll be a value. This is going to put out a number that is a value between 0 and 1, not 0 or 1. It's going to be like 0.534. And then we can just say, well, over 0.5, that's true. Less than 0.5, that's false. Building a binary model. We're just going to set it up and get it running and see it in action now. Except I got farther than I should have gotten. No, command not found, not deact. What are you telling me right now?
Are we doing this in a Jupyter notebook or does it matter?
I will open up a Jupyter notebook file. It doesn't matter. I find it's a little bit easier to display this, but I don't particularly like Jupyter notebooks. It's just easier to run it one thing at a time, and that's what it'll be good for. Blow that away. Make sure I've got this still. Oh, goodness. There we go. Not to just get quiet and lose y'all there, but I needed to use a different version of Python because PyTorch didn't work really well past 3.10, and I was on 3.12, so I went to a 3.9 that I knew I had installed. Oh, and I think I need to install it. So I'm going to create a touch. That's right. VS Code should say, hey, let me help you out with that. Why is it not asking me? There we go. Cool beans. I'm going to select the kernel from the virtual environment that I set up. Now, I'm in a Jupyter notebook. These can look a little weird at first, and you might think, why would I ever do that? Well, they're useful to some people. Data scientists tend to like these things. It's very formulaic. You build a bunch of little code blocks, and then you can run the code blocks. It's just Python in here, right? Hey. Oh, duh. See, I set this virtual environment up ahead of time with the wrong Python version. gosh. Oh no, this is going to take a while. Not off to the races, guys. Goodness gracious.
You want me to share my screen and I can just drive and you can talk? Or do you want to wait for the download?
I forget how long this takes. I think it's in the realm of 3 minutes. I think it's worth waiting for. Let me pause this. Dadgum. No, not that. Recording's resumed. Goodness gracious. All right. We're in a Jupyter notebook. It is just blocks of Python code that we can run. We can decide which kernel we're using. The one I install is what we'll be running. This is just like as if you had set up a Python file and you're running Python on it each and every time. But we're gonna be able to break it up into individual code blocks. Y'all can use this for other stuff. It can be helpful kinda when you're working through algorithms, maybe. There's no reason we have to do it here. I do think it helps kind of break apart these multiple different Python bits we're going to be running through. Okay. So back to building a binary model. Now that everything's actually set up the way I thought it was supposed to be. We're going to import torch, import in. That is the neural network library within torch. It's got some tools. We're going to get slightly familiar with some of these things. Basically, I think sequential is what we're dealing with. But linear, this is a layer, applies linear transformation of the input data. That's about that. You would use that with these bullets, right? Capabilities, linear transformation of input data, cannot capture nonlinear relationships in the data. It's limited to modeling complex patterns without activation functions. Yeah. Hidden layer when placed between input and output layers, and it transforms data through a weighted sum and added bias. Sigmoid activation function maps. This is kind of the same thing we're talking about here. And these terms get mixed up a little bit, but you often hear the activation layer referred to as the sigmoid. Why sigmoid? Don't look at this formula. That's all right, unless it makes a lot of sense to you. It is used for binary classification as it outputs a probability value, which is what we want to do today. Seems good. We're going to define this model. Once this model is defined, we'll be able to peel these layers back a little bit, and it should make a tad bit more sense. We'll be using the neural network library within Torch. What is this? This is defining basically the complexity of our model. We are going to have basically we'll be able to take 3 inputs in. We're going to pass those 3 inputs down to 2 inputs. So our first linear layer is going to take 3 inputs and it will output 2. Second linear layer will take 2, will return 1. And then our sigmoid is going to be our activation layer. We're taking in 3 inputs. We're passing it down to 2 inputs. Those 2 will be with, just 1. And then we will convert that into a binary yes or no. Lost my spot. I don't know that the Y's are super important here. But neural network sequential is a container module that sequences a series of layers in a linear stack. It simplifies the model building process by allowing you to define the forward pass of the network into a straightforward manner. Basically, we're saying you're going to go from 3 to 2, you're going to go from 2 to 1. We have a little bit more control over these things. Utilizing the sequential model. This is a lot of hoopla to tell you. I have built my first linear layer to accept lists of 3, which means this is good. This is good. This is a list of 3 integers. Also, we'll get down to the bottom, they need to be floats as well. So 1 point nothing, that's a good bit of data we can feed in. 0.1, 0.1, 0.1, that's fair. This is good as well. We've got 5 things, but we can only, our activation layer is only going to accept 3 basically arguments is the way we're going to look at it. And you don't have to take my word for it. We can just, I'll copy paste a bit. Let's run that. In a Jupyter notebook, anything you've done in a different code block is not an isolated code block. It's treating it like a giant page. You just don't have to run each block every single time. So this has been ran. Everything that outputs from this block is now available in this block. We don't have to rerun the entire file again. So
Jordan,
our model, yes.
I have a question. What are you using to determine the values?
Nothing. These are completely random.
Okay.
I am showing you these need to be floats, and there needs to be 3 of them. That is what I want you to take away.
Okay.
Input tensor uses torch to utilize tensor to build these matrices, or rather to treat it right like a matrix. We then will take the output of that tensor and plug it into this model. Our model, which is defined here, the 3 layers, 2 layers, and 1 layered out. We're going to plug in this matrices from tensor into it. Great, looks good. What is the output of this, though? I wonder. Oh, oh, goodness gracious, Jordan. Already forgetting our basic Python. What are these numbers? That's the activation layer. For each of these 3 that we passed in, we have ran through our 3 layers or 2 layers or 1 layer. And based off of random numbers, I know it's like, what is it doing? They are random numbers. We are not deciding whether this thing is a hot dog or not a hot dog. We don't even know where to start, but we're starting at random guesses. And this doesn't know if it's right or not. With random guesses, that's where we're at. We have to start here. We have to start at randomization before we can move on. Because if you ask somebody who didn't know what the number 8 was, they're just going to say, I think it's an 8. I don't think that one's an 8. And then we're going to have to come back later and say, well, that's an 8 because that one's not an 8 because. But that's what this is. Greater than 0.5 is yes. Because we tell it so. If the output is greater than 0, or sorry, greater than or equal to 0, it's true. Less than or equal to 1, wait, well, the math, greater than 5, true. Greater than 0.5 is going to be true. Greater than less than 0.5 is going to be false. That's the way we're going to do it. This is numbers. Computers care about numbers. It's going to be weighted towards, I think it's likely false. I think it's lightly true. That is just an output of, I am 55% sure that it is a true value. I am 44% sure it is a true value. Let's call it false. That's what these numbers output.
Jordan,
Yes.
I'm just trying to understand the process. So this matrix here, in a sense that we are passing into the layers, this would be the representation of the image that came in and then was converted to these values that we are sending to the layers.
Yeah, and that's a good way to think about it.
Okay.
In that example, yes, this would just straight up be like, I mean, if we wanted to take a stab at it, right? Like you can, it's a matrix, we can picture it. I think they have to be whatever's. We'd say, oh. I'm just trying to draw an 8, y'all. Um, oh, in 0.1. So use our imaginations. Did I miss one? 0.1 is blank space. 0.2 is darkness. It's my drawing. Remember, this is a super low pixel screen here. If I were to draw an 8, 0.2, 0.2, 0.2, 0.2. You follow what I'm doing here? This is a circle of 0.2s. This is a circle of 0.2s. That is the matrix output. That is the representation of an 8. Okay? We can run this thing again and see what it does. It's not going to be the most useful. Are we getting a different output? What? As expected. Maybe it's just going to guess the same things. And that's okay. That doesn't matter super much. But this would be the representation of the 8 I have printed on this screen, the picture I have sent it, and that is how it's looking at this input. This would be a good way, I guess. It's probably way more numbers than this to determine pixels on a screen, but this gives you an idea of the image it's looking at, how I could take an image and turn an image into numbers to then do some work with, right? So looking at an 8 on a screen, I am deciding 0.1 is blank space, 0.2 is something else, and we're passing it in. Does everyone at least follow with that? That's probably a good way to start this in the future. All this junk is its best guess of whether it was a yes or a no. Why are they random ass numbers? Because it's random. It's taking guesses and it doesn't have any context. It doesn't know. But I want you to I'll show you where these numbers are being generated from. Because we decided the input, we decide what the output means, but until we train it, this is just taking really bad guesses. And we're gonna, based off of what we get out of it, we're gonna be able to come back and say that was a bad guess or that was a good guess. Let's adjust your formula a little bit to get you to point where you're supposed to be pointing. Again, computers don't know. We're having to talk about all this context. And that's why I started with a stupid example of telling Sean to pick out which is an 8 and whatever. If, what if it accidentally got this? Is that close enough to an 8? It might be. It might not be for us. And we would have to adjust to that and say, hey, that's not an 8. I know it seems close, but it's not. So then the formula would have to be adjusted to get those numbers even closer and tighter. But that's more or less the training that we'll be doing later. All this to show you, these numbers won't be allowed. I can try and run this. As we said before, our activation layer takes 3 things. It can't be 4 things. So if I run this, we're going to get a weird output of runtime error, output model, a bunch of junk. Mat1 and Mat2 shapes cannot be multiplied. 3x4 and 3x2. 3x2 is what I said our model is. So it can't be a 3x4. Also, they need to be floats. This will break it as well. Yep, it's unhappy with us. Mat1, Mat2 must be same D type, but got log and float. That's just the error you're going to get. So bunch of stuff going on here because we established it's a 3x2. It needs to have 3 arguments at a time. List needs to be 3 long, has to be a float. That's the error you're going to get. Don't lose your mind if you see such an error. That's all it is. It's not a scary problem. Yeah, so we have done this, and that's what I'm doing with each of these. there's still, abstract things here, and I'm talking about these random numbers. I'm saying, formulas and whatnot. We can demystify it a little bit, and I can see what actually is going on with this model here. Name parameter. Hold on a second. For name param. I mean, this will run, but I'm trying to. All right, there we go. Oh, duh. So looking at my model, don't forget, and this is the part I don't super love about notebooks, is you make a big mess. And I forget how to clear it out. Bam. Junk. There's probably better ways to interact with that.
If you hit those three dots over there by the output, it has option to clear on the left, like where it says like zero weight, the on
Oh,
underneath.
hey.
Yeah, right there.
Sick. All right, cool. I don't want to say this has changed since I played with it last, but it very likely has changed. What is this junk? These random numbers that I've been talking about, these random calculations that are doing this magical work, well, they're not so magical anymore. This is them. We've got our first weights for our first activation layer. 0. It's our first one. And we've got our biases. For our second, we've got these weights and we've got these biases.
I've been following along kind of same line as you, and I'm getting different numbers. Is that normal because of that Sigmund?
Because they're all random.
Okay.
When I created this right here, these random numbers of our weights and our biases were assigned at that point. So yours will be very different. I won't get the same as this lecture. Probably, I don't know what the chances are. It's just not going to be that way. This is this random guessing, right? Again, our model is brand new. He was born today. He doesn't know the concept of an 8 or what it could be. He's just guessing, right? That'd be like if you were putting someone on a game show in Russia and they did not speak Russian. You're going to just kind of guess until you get it right. That's why we're taking random guesses at first.
Okay, and the parameters are that he's guessing in are those input tensor then, right? That matrix?
No, the input, that matrix is the input. That's the letter 8, right?
Okay.
All of these are all the different things that fire off in your head as to whether you're going to guess yes or no. This is the decision making going on here. Weight being, well, that looks like 8s. Biases being, well, I guessed 8 last time and I wasn't right. Notice there's going to be twice as many weights and biases on the first activation layer than the second. We're getting smaller each time. The math itself kind of shows you how the sausage is made a little bit. All we're doing, see, this 0.1, 0.2, 0.3. For our example, it would be that, oh, I got rid of it, but the 0.1, 0.2, 0.1, whichever. We're saying the very first layer, or the very first argument in our input. That will be multiplied by our first set of weights right here. And then added by our biases. Meaning these numbers here are the formula, right? It is making some wild guesses saying, hey, if I multiply this list by my 2 separate bias lists, and then I add, my weighted list, and then I add a bias to it, that's how I got my guess. adjustment of these numbers is what the training is going to be. Saying, hey, yeah, those numbers are crap. That's a bad guess. If it's 0.1, 0.2, 0.1, that's always a yes. All these should just be a 1, right? It needs to come out as a 1. That's 100% right. No doubt about it. You're not going to be coming in and adjusting these numbers manually. There's better tools for that. But this is what this determination process is. This is yes, hot dog, not hot dog. Mathematically, how it decided based off of the pixels we handed into it. This is the decision making going on. Computer has to use numbers. We're using numbers with our neurons. We just don't think about it. All the different times that you see the very first layer of pixels, you can take a guess. Hey, that looks like the start of an 8. Hey, the rest of those match an 8. Hey, that's definitely probably an 8. This is a mathematic representation of what that is. I don't expect you to do this math and be like, yeah, that math checks out. But this is what it is. This is just demystifying what's going on here.
Jordan,
Yes.
I have a question. So you were talking about numbers being adjusted. There's software to handle that. The question I have is, where is the data being stored for that it's learning? I mean, I already know it's in RAM, but I mean, because if we didn't save it, wouldn't we have to keep training it over and over from the beginning?
It's saved right here in this variable. Right? I showed you this is how the sausage is made, right? These numbers are not going to change every time I run this. When I created it here, these
Uh-huh.
values were created. They're right there. That's it. That's what they're going to be.
But
Which
but if you're saying that we're having to train a model and you gave an example of a hot dog, right? We're saying
yep.
yes, yes, no, this is it, this is that, right?
Mm-hmm.
When we shut this down, right? And when we go to spin it back up, is it going to remember those values? Like, where is that data being stored at? Because if not, won't we have to start all back over from the beginning?
Yeah,
That's
that is
what.
something we would stay that I mean these things get massive, right? Like
Yeah.
this is a little baby that we've got, you know, 3 neurons to 2 neurons to 1. This is it. You've
Mm,
seen all of these formulas right here. This is all the numbers that come in to get us an output.
mm,
A small machine learning, I guess model, you're going to have 700 of these first ones, right? You're going to have a ton of lists of numbers. We'll store that in code for now, right? We'll store that in source control. This number is going to be saved somewhere. But as these things get larger and larger, it's going to have to get stored on exponentially larger disks.
So it's the values that we are seeing, like here per se. Let's just say, okay, yes, this is a hot dog. So that this a particular set of values is what's being saved. That's
Yes.
what you.
Assuming
Okay.
we save it. Right now, if I kill this file, that's gone, right? You're absolutely right. It's being saved in memory right now.
Yeah.
This is not a sustainable way to develop on this. This is just seeing it alive in action. I'm in a Python shell right now, technically.
Okay. Thank you.
Mhm. The math of it, we're multiplying the input by this, using tensor to help us out with that, multiplying matrices with other matrices. We're then adding it to these values, right? We have 3 different things coming in. We have 3 different, weights, lists of weights that are going to get it down to 2. and a bias for each of those two. For our second layer, we're taking 2 down to 1. We have 2 weights, and then we have the bias that we're going to add to it, right? Every time it goes through a layer, it's being multiplied by the weights, and it's being added to the bias. Multiplied by the weights, added to the bias. Not all neural networks, you can think of it as fizzling out, like they die here. Yeah, they're either going to be lit, as in, yeah, you're good, or they stop dead there. So if you see a massive, I'm getting too down in the weeds on that. But that's the math going on. That's all I want you to understand. These random numbers that are created are not so random, like they're not ever changing. They're set, and we can see those. And if you want to see them, you literally just like this model is an object, right? I can print that object probably. Yeah, it's just a representation of an object. Actually, this is going to be more correct. There we go. That's what you're used to seeing. This model, at least the name parameters, the layers, right? This is just an object. Like you would do with any other Python object, we can still iterate through it. We can still key value pairs. That's all it is. It's just an object that's been created with random values. The sigmoid is basically taking all that and saying, hey, I need a number between 0 and 1. That's all this math is doing. 0 to 1. Remember our output. Now, do we run it again? Let me grab some output real quick. Gordon. This number here, between 0 to 1, greater than 0.5 true, less than 0.5 false. That's what we're looking for. The sigmoid is just doing that for us, giving it a 0 to 1. There we go. And then we can decide true or false, right? I see a 5, 6, 4, 1. That's true. It's greater than 0.5. Still 0 to 1, right? Setting weights and biases. Although not recommended, there may be a time where you'll need to set the weights and biases manually. We can do that. Again, like I said, we won't, but you can. We're going to go in and say, hey, by the way, those weights and biases suck. I want you to replace them with this. Is this not happy with space there? Oh, okay. Well, great. So ideally, that changed those weights. Let's verify. Heyo. These random weights that we were assigned, oh, we changed them. Just like that. You can do that. Again, this is not a, you would not want to get to this level of granularity trying to train your thing, whether it's a hot dog or not a hot dog, but you can. These things are set. They're adjustable. They will be adjusted with better tools in the future, but look, they can be changed. It's not nothing set in stone. All of this was kind of scripted, right? Just setting a variable, building a model out of it, and having a variable. That's baby stuff. We instead are going to use object-oriented programming to set up that model as an actual class, so we can interact with it more Pythonically. Everything I've done before is represented here. Now it's happy. We took the neural network module. We created us a new class called binary model. You have to super init because we are using a model to create our class, right? This is just inheritance, right? From a class that already exists. There it is. We're setting our first linear layer 3 to 2, second linear layer 2 to 1, and we have a sigmoid. That's just what we did up here. And then the forward is basically telling it, hey, pass it through each of these linear layers each time, right? It goes through linear layer 1, and then 2, and then the sigmoid, and returns. These are established. They're created. When I run this class, when I instantiate this class, all these things are set. This is a little bit easier to interact with, I would say. But it's a Python object now. You should be able to run all these same things off of it. Still interacts exactly the same. I think we probably could have started with the class, but maybe it's good to see it line by line first. We can add more layers to this. We can inspect these parameters as we see fit. Generate a simple synthetic data set. Y'all saw me build an 8 out of a matrix with lists of 3 and 5 of them. Get creative on what you think an input would be. It's really up to us as the developers to decide what the input is or to take the input, right? If we're doing image recognition, the machine learning, the neural network is going to be able to make decisions yes or no based off what we tell it, but we decide what it's going to ingest, right? It's just a function. It's just a big function, right? We decide how that data comes in, and then we tell the function whether or not that was right. Dare anyone ask questions?